3B, measures of spread. Okay, so last video we talked about measures of center, which was where the middle or the center of our data is. Now we're going to look at the spread on it, because it should be pretty obvious to you that there can be different sets of data, very different sets of data, that have the same centers, but very different spread. I could have two sets of data that have an average of 100. One could start at 50 and end at 150 and have an average of 100, or I could have one that starts at 98 and ends at 102 and has an average of 100, right? So just having a measure of center doesn't give us the full set of information. We want to look at the spread also. Well, let me get a set of data up here, and I'm going to make it a small set just because it's going to make some calculations easier for us. And in reality, I'm probably not going to pound you with tons of data when doing these calculations because it just gets repetitive. Let's say I have 56, 72, 64, 59, 65. So I've got 5 data values. My first measure of spread that I'm going to do is my basic measure of spread, which is just the range. And we've already done the range. Range is just the max minus the min. Remember, we did that for doing our frequency distributions. So our maximum value here is 72. Our minimum value is what? 56. (72 minus 56 is 16. So we have a range of 16. So that's our basic thing. How big is the spread of our data? Well, the range is such and such. So that's a very basic one. Our second one that we look at is the deviation. And I'm going to start with population deviation. So our population deviation, well, what's our easiest comparison we can do? Well, really, if I were to ask someone, are you tall or are you short? What's the comparison they're going to use to determine that? Well, they look around and say, well, in comparison to others, am I taller or shorter than them? And the best comparison we can use is comparing to the mean, the average. If you're taller than the average individual, then you are tall. If you're shorter than the average individual, then you are short. Okay? So population deviation is found by taking the data value x and subtracting the mean. So that will give us our deviation. Notice that this is for an individual point. So x minus mu for an individual point. Well, we've got 5 data values here, so what's that going to do for us exactly? Well, I can do a quick comparison and say, okay, well, what about this 56? Well, what's the average of my 5 data values here? So I've got 56, 72, 64, 59, 65. Add those all up, get 316, divide by 5, and I get 63.2. So I could say 56 minus 63.2 gives me negative 7.2. Okay? And if I were to take 72, I'd have 72 minus 63.2, which gives me 8.8. 64 minus 63.2, 0.8. 59 minus 63.2, negative 4.2. 65 minus 63.2, 1.8. Right? So each one of those has its own deviation. So if that's the case, I need something that's going to bring all of this together. because that's nice, everyone does, but I want a single number that's going to give me a measure of spread for this whole thing. So how am I going to do that? Very simply, I'm going to find what's called the standard deviation. Now the population standard deviation, we use a Greek letter sigma to represent that. Yeah, it looks like an O with a tail on it. Okay, so we use Greek letter sigma, and the formula is the square root of the sum of x minus mu squared over n, the population size. So the sum of x minus mu squared over n, the population size, take the square root of all that. Order of operations says take x minus mu, find the deviations, square them, add them up, divide by the population size, and then take the square root. Well, as nice a formula as that is, that's not exactly what I want to do to find the population standard deviation. So let me move this formula up to the corner so that we can still have it here and give myself some space. Then I'm going to get rid of these, and what we're going to do is we're going to build a table. So we're going to build a table to do this, so we're going to start out and we're just going to list out our data values x. So we got 56, 72, 64, 59, 65. And we're going to find x minus mu. Well, if we want to take each data value and subtract the mean, we need to find the mean. So we're going to sum those up, and I know we already did that, but I'm going to do it again because I think I have it as 63.2, but I don't want to have the wrong number there. So it was 60, oh, sorry. So that summed up to 316. So mu is equal to 316 divided by 5, which is 63.2. So that is our population mean. So now 56, so 56 minus 63.2. Just going to do the first one like this to demonstrate what's happening. So 56 minus 63.2 gives us negative 7.2. 72 minus 63.2, and just don't want to make any stupid mistakes here, so I'm just going to throw that into the calculator. And it is 8.8 like I said before. 64 minus 63.2, 0.8. 59 minus 63.2, negative 4.2. And 65 minus 3.2, 1.8. So now I have my deviations. Remember, I want all my deviations. Now what happens if I add those up? If I add up my deviations, negative 7.2, 8.8, 0.8, negative 4.2, and 1.8, they add up to 0, and rightly so. They should add up to 0 because we're comparing each data value to the mean, the middle of the data. So to get that mean, they should be equally balanced on both sides. So all of our negative numbers should add up to the same amount as our positive numbers. Now we may not be exactly 0, we could be something really close to it. If we had to round our mean, then that could affect these slightly. Just like we saw with relative frequencies, percents, and degrees when we were dealing with qualitative data and creating the pie chart. So that same thing could happen here, but we are looking for this to be 0. Next thing we're going to do is it says that we need to square each of those. So x minus mu squared. So we've got 7.2 squared is 51.84. 8.8 squared, 77.44. 0.8 squared, 0.64. Negative 4.2 squared, 17.64. And 1.8 squared, 3.24. Now let me just take a moment and point something out to you. Notice we squared a negative number, we got a positive result. Squared a positive number, we get a positive result. Positive squared gives you positive. Negative squared gives you positive. All of these numbers in our squared column have to be positive. Be careful, because a common thing for people to do is they go negative 7.2 squared, they plug that into their calculator, and their calculator order of operations says 7.2 squared is 51.84, and then it negates it and makes it negative 51.84. To put in your calculator correctly, you need to tell it that that negative is being squared also. Or, do as I do, I just don't bother plugging in the negative, because I know if I square a negative number, I get a positive result. If I square a positive number, I get a positive result. So why waste the time plugging in the negative? So that's my x minus mu squareds. Now it says to sum them up. So I'm going to add those up, which gives me 150.8. So that's my numerator here. The sum of x minus mu squared is 150.8. Now we're going to divide by n. Let me just put that up there for the sake of having it written on the board. Right, there's 5 data values, so our population size is n. So we're going to divide that by 5. And we divide that by 5, we get 30.16. Sorry, I lost my 0. 30.16. So that's everything in the radical, and that is sigma squared, right? If the square root of something is sigma, then before you take the square, you must have sigma squared. That sigma squared is known as the variance, so that would be the population variance. This is another measure of spread that is sometimes used. Be careful and make sure that you're looking for the right thing. And then to find our population standard deviation, we just take the variance and take the square root of it. My favorite formula, sigma is equal to the square root of sigma squared. X is equal to the square root of x squared, right? If you square something and then take the square root of it, you get back at whatever you started with. So sigma is equal to the square root of 30.16. So the square root of that is about 5.49. So sigma is equal to 5.49. So our population standard deviation is 5.49. Now that took a little bit of work, but trust me, it's going to be more accurate and faster than just going through your piece of paper and doing x minus mu, x minus mu, x minus mu, x minus mu, and then adding them up and everything. This keeps it organized. They work out well. You have your sanity check along the way to make sure that everything's good. You make sure you didn't come out with any negatives here, because when you do, it screws everything up here. Okay, so that would be bad. Make sure you divide by the population size, and then take the square roots and get the standard deviation. Before you take the square root, you've got the population variance, sigma squared. So I did all this for treating this as a population. Well, we have the same things. We have sample variance, sample standard deviation, sample deviation. So all the same things occur, but it just barely changes what happens here. So what I'm going to do is I'm going to take a red marker, and I'm going to adjust for what happens if we were to treat this as a sample. it does not change much. Let me get the calculator off to the side here. If this is a sample, then we no longer have mu, we have x bar. We no longer have mu, we have x bar. But remember, you calculate the sample mean the same way as you do the population mean. It's just a matter of whether you're dividing by population size or a sample size. We obviously now are dealing with a sample, so lowercase n is equal to 5. This still all calculates out the same. This becomes x minus x bar. Okay, so I'm going to come over here, I'm going to change this a little bit, because there are three things that change with this. The first is that for a sample standard deviation, we use the letter S. S. That's not a 5, that's an S for standard deviation. So that's a sample standard deviation, x minus x bar squared. And the other little change is it's not just divided by n, but it's divided by n minus 1. So lowercase n minus 1. So we do this, we have our n, x minus x bar, we get to this. At this point, we have divided by, well, sample size is 5, 5 minus 1 is 4. So divided by 4, so now grab the calculator. So 150.8 divided by 4 gives us 37.7. And that gives us not the population standard deviation, sorry, not the population variance, but the sample variance, which is s squared. So the sample variance, s squared, is 37.7. And then when we come up here, we get s is equal to square root of s squared. That is an s, not a 5. So s is equal to the square root of 37.7. Or s is equal to 6.14. So notice that when we change to dealing with a sample, most of it stays the same. We change variable names, mu becomes x bar, capital N becomes lowercase n, mu becomes, sigma becomes s, right? Sigma squared becomes s squared. But in the actual calculations, the only real difference is that instead of dividing by the population size, we divide by the sample size minus 1. So just that little modification take us to a sample variance and a sample standard deviation. Now, why do we make that change? Well, I could go through a whole bunch of calculus to show you the proof of why that happens, but I'm going to go for the simple explanation, which is just that if you take a sample and do the calculation and divide by the sample size, then you tend to underestimate the population standard deviation, meaning your sample standard deviation tends to be too low. Whereas if you subtract 1 from it, from the sample size, then your sample standard deviation tends to better represent your population standard deviation. So that's the simple explanation of why we do this. Now you can also do this using your calculator. I'm not going to show you how to do that. You can look that up online. But you can plug this into your calculator and get it. I really want you to do the work by hand at this point. When we get later on in the semester, you're going to do some things that it's really handy if you can just plug into your calculator and get the standard deviation or the variance. And any scientific calculator will do that for you. Okay? So that's dealing with those. What I'd also like to do is just putting my calculator down is look at some other things dealing with spread. Sorry, going out of screen for a moment here, because I want to get to the empirical rule. Now, we're really dealing with a symmetric distribution at this point, or assuming that things are symmetric when we start to deal with the empirical rule. The empirical rule is based on the fact that a normal distribution is symmetric it has a mean, median, and mode at that center point, and that it can be defined by the mean and the standard deviation. You give me a mean and a standard deviation to any normal distribution and I can draw it for you. Now remember, it's symmetric, which means that if I fold this over on the dotted line, it's going to be the same on both sides. That means half of the data values are greater than the mean, median, and mode. Half of them are less than the mean, median, and mode. It also means that certain things are going to happen at certain places in this distribution. So I'm going to get rid of that under there, and I'm just going to say that that's the mean, mu. And I'm going to start talking about things that happen in this distribution. For any normal distribution, give the mean and the standard deviation, one standard deviation away from the mean is going to be an inflection point. An inflection point, an inflection point. Now there's a difference in what I just said there. An inflection point. That's making a statement. An inflection point, I turned it into a question by the inflection in my voice. It's the curvature or the bend. Now if we look at a normal distribution, a bell curve, look at the shape, you see that it does this. And if you look carefully, you can see that there's a point where I'm drawing an upside down U. And at some point it switches to where I'm drawing a right side up U. Notice that? Upside down, right side up. That transition from where it goes from an upside down U to a right side up U, that is the inflection point. That inflection point occurs one standard deviation away from the mean. So if I call that the inflection point, that occurs at mu plus sigma. It's one standard deviation from the mean. It happens on the other side too, mu minus sigma, one standard deviation away from the mean. According to the empirical rule, 68% of the data is within one standard deviation of the mean. So from mu minus sigma to mu plus sigma. In that range, you'll find 60% of the data for any normal distribution. If I go out another standard deviation, so I have mu plus 2 sigma and mu minus 2 sigma. So now I'm 2 standard deviations away from the mean. According to the empirical rule, that will include 95% of the data for any normal distribution. And finally, if I go out a third standard deviation, so mu plus 3 sigma, and mu minus 3 sigma, according to the empirical rule, 99.7% of the data will be within 3 standard deviations of the mean. And for that reason, the empirical rule is sometimes referred to as the 68, 95, 99.7 rule. I know, very creative. Because 68% of the data will be within 1 standard deviation of the mean, 95% of the data within 2 standard deviations of the mean, and 99.7% of the data within 3 standard deviations of the mean. Well, that's great, but who cares? What does that do for me? Well, it actually does a number of things for me. First of all, it means I can start determining where my data is located. Secondly, it means that my data is very consistent for normal distributions no matter what my mean or standard deviation is. If my mean is 100 and my standard deviation is 5, then between 95 and 105, I'll have 68%. If my mean is 100 and my standard deviation is 50, between 50 and 150, I'll have 68% of the data. But let's take a little look at this and redraw this normal curve here and define a mean and standard deviation and see what we can do. So if I have mu equal to 100 and sigma equal to 15, which is the mean and standard deviation for the population of IQs. An average IQ is 100, the standard deviation is 15 or 16 depending on which method they use to do the calculations. I believe 2 of them use 15 and 1 uses 16. So if I've got that, I can build my distribution. So I start out, my mean is 100. Awesome. Okay, my mean is 100. If I go one standard deviation above, it's 100 plus 15, or 115. And if I go one standard deviation below, it's 100 minus 15, or 85. If I go 2 standard deviations, 115 plus another 15 is 130. 85 plus minus another 15 is 70. And if I go out a 3rd standard deviation, then 130 plus 15 is 145. And 70 minus 15 is 55. So I just laid out the normal distribution for IQs. Well, that's nice, that's cool, that works well. But what does it do for me? Well, now, if someone asks me the question, what percentage of IQs are between 70 and 130? I go, here's the mean, here's 70, here's 130. That's 2 standard deviations to the one side, 2 standard deviations to the other side. So within 2 standard deviations of mean, the empirical rule tells us that 95%. So 95% of IQs are between 70 and 130. What percentage of IQs are between 85 and 115? Between 85 and 115, that's 1 standard deviation. 1 standard deviation. 68%. Between 55 and 145, 99.7%. And to go even a step beyond that, we can break it up a little more because we know that this is symmetric. So we can say that if I go to only one side of the mean, 1 standard deviation, then 68 divided by 2 is 34. So 34% is within 1 standard deviation to one side. Half of 95 is 47.5. 47.5% is within 2 standard deviations to one side. And half of 99.7 is 49.85. So 49.85% is within 3 standard deviations to one side. Which means I can go even further and say, what about between 85 and 130? Well, that's here and here. That's 2 standard deviations above and 1 standard deviation below. So I can't use the strict empirical rule because that would be, has to be the same on both sides within 1 standard deviation, within 2 standard deviations. But now I can say within 2 standard deviations to one side, well, that's 47.5%. Within 1 standard deviation to one side is 34%. If I add those together, I get 81.5%. And there we go. So it can be really handy to be able to do this. And that's great if you have a normal distribution. Unfortunately, we don't always have that. At times we have a non-normal distribution, which is anything that's not normal. It'd be great if everything looked like this. You know, a nice bell curve. But instead, the real world many times looks more like this. Right? That is not a normal distribution in any way, shape, or form. So I can't use the empirical rule for this. But thanks to Chebyshev, a man with way too much time on his hands, but a very intelligent person at that. So Chebyshev, and I'm going to call this Chebyshev's inequality. If you don't remember, an inequality is anything that deals with less than or greater than, right? So Chebyshev said, well, yeah, that's great, we can do this for a normal distribution. Well, what if we're dealing with a non-normal distribution, some other random shape? And he came up with a method for determining the minimum percentage of data within a certain range. So it's not the exact amount, but you could say at minimum there will be this percentage of data. And to do this, so this is for a non-normal distribution. Let me just clarify that. I'll put that over here. So this is for a non-normal distribution. He said 1 minus 1 over k squared, where k is greater than 1. That's his equation. Took a lot of time and effort to come up with this. K is with the number of standard deviations, within a certain number of standard deviations. So within k standard deviations. STD, standard DEV deviations. So within k standard deviations. So he said this will work for any distribution, whether it's normal or not. So let's take a look at it and say, what if we set k equal to 2? What percentage of data values, at least what percentage of data values can be found in that? So k is equal to 2, then we take 1 minus 1 over 2 squared. 1 minus 1/4 gives you 3/4, or 0.75, which gives you 75%. So it just, at least what percentage of data is within 2 standard deviations of the mean for any distribution? 2 being 2 standard deviations, k. 1 minus 1 over 2 squared is equal to 1 minus 1 over 4 is equal to 3/4 is equal to 0.75 is equal to 75%. So Chebyshev said that at least 75% of the data will be within 2 standard deviations of the mean, no matter what distribution you're dealing with. Well, what if we set k equal to 3? So I'm going to set that equal to 2 there. We set k equal to 3, so what percentage, at least what percentage is within 3 standard deviations? Minus 1 over 3 squared is equal to 1 minus 1/9 is equal to 8/9 is equal to 0.8 repeating is equal to approximately 88.9%. And we can do that for 2, 3, 4, 5, 6, however many standard deviations. Now, if you remember with the empirical rule, it said that for a normal distribution, at least 95% of the data is within 2 standard deviations of the mean. Or sorry, 95%, not at least. 95% of the data is within 2 standard deviations of the mean. Chebyshev says for any distribution, at least 75%. 95 is definitely over 75%, so it fits into what he said. For 3 standard deviations, the empirical rule said at 99.7%. Chebyshev says for any distribution, at least 88.9%. Again, 99.7 definitely fits into that range. So once we have this knowledge, we can now do the same type of problem that we just figured out dealing with normal distributions. Say, well, what if we have a non-normal distribution with a mean of 57 and a standard deviation of 6, at least what percentage of data is between 39 and 85. So at least what percentage of data is between 39 and 85. So how would we find that? We create a distribution, and I know it's not necessarily a normal distribution, but it's easiest for me to draw something like this to envision it. So my mean is 57. If I add the standard deviation, I get to 63. Add another one, 69. Oh, I went too high. That was supposed to be 75. Sorry about that. Another one, 75. If I subtract the standard deviation, I get 51. Subtract another one, I get 45. Subtract another one, 39. My mean was 57. 39 and 75 is what I was looking for. That's 3 standard deviations. 3 standard deviations. So basically we're asking at least what percentage of data is between 39 and 75, so at least what percentage of data is within 3 standard deviations of the mean, and that's where we did 1 minus 1 over 3 squared is equal to 1 minus 1/9 equal to 8/9 equal to 88.9%. So at least 88.9% of the data is within 3 standard deviations of mean, or between 39 and 75. Now, how do you tell when you can use the empirical rule and when you can use Chebyshev? Empirical rule, when it states that it is a normal distribution. Chebyshev, when it does not state it's a normal distribution. So if it says non-normal for any distribution, if it does not state normal distribution, then you use Chebyshev. One nice thing about Chebyshev, we cannot run into that imbalance. Remember, we had the imbalance before, that with the empirical rule, that I could have it go more to one side than to the other. That cannot happen with Chebyshev, so it's got to be nicely balanced. It's either 2, 3, 4 standard deviations. It can't be 1 to one side and 2 to the other. Another thing I want to point out about the Chebyshev inequality is that k has to be greater than 1. Why? Common sense. If k is equal to 1, we have 1 over 1 squared, which is 1 over 1, which is 1. 1 minus 1 is 0. And I think any of us could say that within 1 standard deviation of the mean, there's at least no data values. So obviously it has to be a value greater than 1. Final thing for measures of spread, the coefficient of variation. So the coefficient of variation. Coefficient of variation, very straightforward. We use CV. And basically what the coefficient of variation does is it compares the spread to the center. So it's sigma over mu. The standard deviation over the mean. And we can think of it this way. If I were to offer somebody in the class $10 and say, okay, here I'm going to give you $10, and they go, great, thank you. and then I come up to them and say, hey, can I have $5 of that back? Now, granted, they still get $5, but boy, why did I bother giving them $10 if it was going to take $5 back, or it took half of it back, right? A large portion of it. Whereas if I give someone in the class $1 million and say, hey, can I have $5 back? They won't even bat an eye with that one, right? They won't blink, they won't do anything. It's like, you just gave me $1 million, sure, have $5, chump change, right? So in comparison to $1 million, that 5's nothing. But in comparison to 10, it's a lot. So coefficient of variation does the same thing. If I have a distribution with a mean of 50 and a standard deviation of 12, then my coefficient of variation is going to be 12 divided by 50, which is, sorry, I have to pull that calculator out, 0.24. Oh, should have been able to do that without the calculator. Okay? Whereas if I have a mean of 1,078 and a standard deviation of 342, notice my standard deviation is huge compared to the previous standard deviation, but my coefficient of variation becomes 342 divided by 1,078. Cannot do that one in my head. Which gives me approximately 0.32. Okay, so which one has more spread compared to their mean? In this particular case, this one did. It had a little more spread, but look at the difference comparison. 342 compared to 12. But it was what it was related to the mean. In comparison to its mean, it was much less significant than it would have been compared to this mean. So that's the coefficient of variation. It's just the standard deviation divided by the mean.